You know, every time you look up, the sky is telling a story. Sometimes it's a gentle whisper, and other times, well, it's an absolute roar. So today, we're going to follow the incredible journey of precipitation, from a simple drop of water all the way to a destructive ball of ice. Let's get into it. You've probably wondered this at some point, right? Why is it that some days we get a soft drizzle, and other days it's a total downpour or even ice falling from the sky? Well, it turns out it's not random at all. It's all about the wild and kind of perilous journey that water takes as it moves through our atmosphere. Think of this slide as our roadmap for today. These are all the possible endings to that journey we just talked about, and you'll notice a lot of them have these size ranges. That's because, unlike something made in a factory, raindrops and snowflakes form in a really chaotic environment, which means you get a huge variety of sizes. We're going to explore what makes each one of these unique, starting with the simplest path of all. All right, so let's start with the most familiar path. Precipitation that forms as a liquid and stays a liquid all the way down to the ground. No drama, no freezing, just a simple fall to earth. But even in this simple journey, there are some really key differences. Okay, so the main difference between mist, drizzle, and rain, it's really just size. Mist droplets are so incredibly fine, they almost seem to hang in the air, and they can make it really hard to see. Drizzle usually comes from those low sheet-like stratus clouds and just makes you feel kind of damp all day. But for real rain, you need drops that are big enough for gravity to really grab onto, born from those thick, moisture-packed nimbostratus clouds or those towering thunderheads, cumulonimbus. But what happens when the journey gets cut short? And that brings us to this really cool phenomenon called virga. It perfectly shows just how tough this journey can be. You've probably seen it before, those kind of ghostly streaks hanging down from a cloud. That's actual rain. Falling, but on its way down, it hits a layer of super dry air and just poof, completely evaporates before it ever reaches you. A whole journey that just ends in mid-air. So, a journey can get cut short by evaporation. But what if the trip not only starts out cold, but stays cold the entire way down? Well, that's when we leave liquid drops behind and enter the absolutely beautiful and intricate world of ice crystals. You know how not all snow is the same, right? It all comes down to temperature and humidity. When it's bitter, dry cold, you get that light, fluffy powder. The low humidity lets those perfect, separate six-sided crystals form, and they just don't stick together. But when it's warmer, closer to freezing, and more humid, those crystals get partially melted and sticky. They start clumping together into these heavy, wet clumps, which, as you know, are perfect for packing a snowball. Now here's a close cousin to snow, rime. This isn't really precipitation that falls from the sky, but rather it's ice that forms directly on surfaces. It happens when things get exposed to supercooled fog. Now, supercooled is a really key concept here. It's water that's technically below freezing, but it's still a liquid because it doesn't have a little particle like dust to crystallize on. So when these droplets finally touch a frozen surface, they freeze instantly, creating these incredible, delicate, feather-like structures. Okay, our journey is about to take a pretty dangerous turn. We've seen liquid and we've seen solid, but what happens when precipitation starts as one and then gets forced to become the other in the most hazardous way possible? It's all because of this strange temperature sandwich in the atmosphere. This right here is the setup for some of the most treacherous winter weather you can imagine. A snowflake starts falling, but then it hits a layer of warm air and completely melts into a raindrop. But then, just before it gets to us, it hits a final layer of air that's below freezing. And what happens in that last little stretch depends entirely on how deep that final cold layer is. So what's the difference? It all comes down to one thing: time. If that cold layer near the ground is deep enough, the raindrop has enough time to completely refreeze into a tiny ice pellet before it hits the ground. That's sleet. You can hear it ticking off your window and it bounces. But if that cold layer is really shallow, the raindrop doesn't have time to freeze in the air. It hits the ground as a super-cooled liquid and freezes instantly on contact, coating absolutely everything in a solid sheet of ice. This is freezing rain, and it is incredibly destructive. To really get a sense of how destructive this can be, we just need to look back at the Great Ice Storm of 1998. For days, a stalled weather front just kept pulling moist air from the Atlantic over the shallow dome of Arctic air that was sitting over Quebec and New England. It created the perfect, sustained conditions for freezing rain. Think about that. For 5 consecutive days, the freezing rain just did not stop. It wasn't a single storm. It was this relentless accumulation, adding layer after layer of ice until the weight just became catastrophic.
The weight of the ice was just immense. Tree limbs snapped like twigs, power lines collapsed, and these massive, high-voltage towers, structures literally designed to withstand hurricanes, they just crumpled under the load. This quote from a Canadian climatologist just perfectly captured the devastation.
This storm ended up causing over $3 billion in damages. More than 1 million households were left without power, some for weeks in the dead of winter. It was just a terrifying reminder of the immense force that can be packed into a single drop of supercooled water. So that ice storm showed us the danger of weight. But the sky's most violent story, oh, that's not about just falling. It's about a chaotic journey up, then down, then up again, all inside the heart of a massive thunderstorm, building a weapon one layer at a time. Every single giant hailstone starts its life as this, a tiny particle called graupel. It's basically a snowflake that gets coated in rime ice as it tumbles around in the cloud, forming a small, soft ice pellet. This is the embryo, the little seed from which a monster hailstone is going to grow. So here's how the monster gets built. First, that tiny graupel pellet gets blasted upwards by an updraft that can be screaming at over 100 miles an hour. As it travels up, it collects supercooled water, adding a new layer of ice. Then it gets heavy, it starts to fall, gets caught in another updraft, and makes the trip all over again. Each trip adds another layer, like an onion, until it's so heavy that even that ferocious updraft can't hold it anymore. The hailstones that come out of this process can be unbelievably large and destructive. But let's put some numbers to that. We're going to look at the largest hailstone ever officially recorded in the United States. It had a diameter of 8 inches. 8! That is larger than a standard bowling ball. Just try to picture that falling from thousands of feet up in the air. And it weighed nearly 2 pounds. This ball of ice, formed by just being violently tossed around inside a thunderstorm, weighed almost as much as a bag of sugar. And this really shows you the danger. It's estimated that a hailstone this large would hit the ground at over 100 miles per hour. Not much can withstand that kind of impact. Not crops, not roofs, and definitely not cars. So you see, from a gentle mist to a 2-pound cannonball of ice, it's all part of the same grand process. A journey with so many different paths and so many different endings. The next time you see clouds gathering, what story do you think the sky is about to tell?